All right, welcome back to lesson 25, speed of light. You know, I've got new respect for people that spend time on the radio talking because it is a lot more difficult than you think. Well, obviously, it's a lot more difficult than I think. You probably know that from listening to my last 2 or 3 lessons. Anyways, regardless, we're on to lesson 25. Lesson 25 looks at the speed of light. Now, we all know all about the speed of light because I use it all the time on sci-fi shows. Speed of light this, speed of light that, going from one point to another. Used to talk about covering vast distances. But before we start on the speed of light, I thought we'd look at something even faster than the speed of light. I don't know if any of you are aware of an awesome movie, Spaceballs, but I thought I'd just show a clip just because I like showing clips.
We're closing in on them, sir. In less than a minute, Lone Star will be ours.
Good. Prepare to attack.
Prepare to attack!
On the count of 3. 1, 2... Late!
What happened? Where are they? I don't know, sir. They must have hyperjets on that thing.
And what do we got on this thing? A Cuisinart?
No, sir.
We'll find them, catch them!
Yes, sir. Prepare ship for light speed.
No, light speed is too slow.
Light speed too slow?
Yes, we're gonna have to go right to ludicrous speed.
Ludicrous speed? Sir, we've never gone that fast before. I don't know if the ship can take it.
What's the matter, Colonel Sanders? Chicken?
Prepare ship! Prepare ship for ludicrous speed. Fasten all seatbelts. Seal all entrances and exits. Close all shops in the mall. Cancel the three-ring circus. Secure all animals in the zoo.
Give me that, you petty excuse for an officer. Now hear this. Ludicrous speed.
Sir, had you better buckle up?
Now buckle this. Ludicrous speed. Go!
Hell was that? Spaceball 1. They've gone to plaid.
All right, so for those of you that haven't seen Spaceballs before, that probably came as a bit of a shock to you. For those of you that have seen Spaceballs before, you know the awesomeness that that whole movie has. I highly recommend it. If you haven't seen it, go out and find a copy for yourself. Now, speaking of ludicrous, let's take a look at how the speed of light was first measured. If we're going to look at a ludicrous idea, we have to first go to Galileo. It's not really fair. He had no idea what he was doing, but let's take a look at what he thought he'd do. Stood on a hill, had another person standing on a hill somewhere else, opened up a lantern. The assistant then would open up his lantern, and based on the time delay, he figured he could calculate the speed of light. Now, really, that wasn't going to work. I got a good graphic that kind of I like to use to show. If you go to the Physics 2000 site, click on the table of contents, there's some good information down here. So we go down to here, measuring the speed of light. Starts off just like we're going to talk about with Galileo. Here he is, turn on his lantern. Dude on the hill turns on his lantern. He figured he could calculate it. Nowhere near the right value. He basically said the difference was basically human error. Let's see if we can figure out why. Let's go with something like the Earth. So here's the circumference of the Earth. We can see down here, it's about 40,000 kilometers. Let's kick up a calculator. So 40,000. We're going to divide this by speed of light. So we should know that that's 3, 1, 2, 3, 4, 5, 6, 7, 8 zeros. All right. Oof, that's off. Oh, wait. 40,000 kilometers. 40, 1, 2, 3, extra 3 zeros to make that meters. Divided by 3, 1, 2, 3, 4, 5, 6, 7, 8. Still pretty small, but much better. 0.13 seconds. So the time it takes for light to travel around the Earth is 0.13 seconds. So Galileo on a hill thinking that he could measure the time, not going to happen. So we have to wait a little while till we have a fellow by the name of Romer about 75 years later. Yeah, 75 years later. What he did is he figured out the approximate speed of light by measuring the eclipse of one of Jupiter's moons, two different locations. They had a lot of astronomical data, so they knew how far things were away from the sun and how long things took to go around in orbits and so on. A really good job. Didn't actually calculate the speed of light, but his data was used to get an approximation. It actually wasn't too bad. The actual work came later, and we'll just kind of pan down here. We'll kind of skip these guys because while they have a good idea, it's really no different than what Michelson did. Michelson he's the man when it comes to calculating the speed of light. He used a distance of about 35 kilometers to calculate it, and here's his apparatus. All right, let's try and explain Michelson's experiment as best we can, as simply as we can. Light travels, hits the mirror, bounces down, hits the curved mirror, bounces up, hits the mirror, goes into the telescope. The thing is, the mirrors are spinning, like a CD player or just anything on a merry-go-round or whatever. So because of that, by the time light hits that second mirror, the angle is rotated just enough that it doesn't go into the telescope. What this means is, if you get a specific rotation, like RPMs, at a certain speed, it'll rotate one mirror just in the right amount of time for it to reflect into the telescope. So what you have there is you have a speed of rotation which you can correlate to the speed of light. So there's a relationship between how fast the mirrors spin and how fast light is actually traveling. It's kind of cool, really. Of course, maybe that's why they gave the dude a Nobel Prize. If we pan down, we can actually see the calculations here. It's the basic v is equal to d over t. You have a velocity, a distance traveled, and a time. The distance traveled is, of course, the 35 kilometers there, 35 kilometers back, 70 kilometers. The t is a little bit trickier to calculate. You have an RPMs, or revolutions per minute. That really is like a period of rotation, which can be correlated back to a frequency, and basically period and frequency, blah, blah, blah. You can see down here, they're able to figure out the speed that it travels. You throw that into the basic formula, v is equal to d over t, and you get 2.99 times 10 to the 8th meters per second. Pretty bloody close. And of course, because he was so close to it, back in 1907, they gave him a Nobel Prize. Cool. That's about it. The point is, if we regress back to the beginning of the speed of light, the original work done by Galileo kind of indicated that they thought that light should have a finite speed. They just had no way of calculating it. Then you had people like Romer and the French people of Fizeau and Foucault, maybe, I don't know, your guess is as good as mine, who did work that was really close, but in the end, Michelson was able to calculate it very, very accurately using basic lab style equipment. I mean, you got a rotating mirror, a curved mirror, and a telescope. That was it. Pretty impressive. Anyways, that's it. There's lesson number 25, the speed of light. Hope you enjoyed it, and we will continue on with lesson 26 later this week.